Okay, so last class we were talking about this example. The difference with example C is that the transmission line now has two circuits, and the fault happened in the second circuit of that transmission line. And not only that, it happened in the middle of that circuit. So if you have a reactance of 0.6 per unit, thank you. I forgot to share now. So if we were talking about this system and the transmission line has two circuits, and the short circuit happened in the second circuit in the middle of that circuit. So if the reactance is 0.6, then the middle of the circuit will split the circuit in the middle. So you will have 0.3 per unit from this point to bus 1 and 0.3 per unit from this point to bus 2. The fault can happen anywhere along this line. It can be very close to bus 1 or bus 2. That is not something we can control. We assume that the fault was in the middle, and by doing that, we realize when we have the short circuit now, the short circuit doesn't make the electrical power that come out of the generator equal to 0. Now, during the short circuit, we will have this power, and we will still be able to send some power to the grid from the generator. So that's an advantage because now the acceleration in the machine will not be as much as the case when the electrical power is 0 during the fault. So we did that, and if we assume that the system is with electrical power described by that blue curve, then the equilibrium point will have an angle delta 0. Then we do have a short circuit in the middle of that second circuit of the transmission line. The power immediately change. Delta 0 remained the same, but because accelerating power at this time is positive, then the angle and the speed will start increasing. So as the angle increases, the electrical power also increase. At this point, we assume we're going to clear the fault, and then by clearing the fault, we remove that circuit from the line. Now the line will have just one circuit to send power. By doing that, the power is increased from this orange curve to the green curve. Now we have more electrical power after the fault is clear. The accelerating power now is negative, and that will at some point stop the increase in the angle and the speed. And we assume that that's the maximum angle we have. And then from this point on, as the accelerating power is still negative, the angle will start decreasing. Our question for you is, what is the speed we have at this point? The maximum angle, what is the speed that we will have there?
The speed of
The machine, omega.
Yeah, a little bit faster than synchronous, but not a huge amount.
If the speed is faster than synchronous, that means that we look at the equation again. Where do we have the equation? We need to go all the way back here. There. So if this is a little bit higher than synchronous, which is 1 per unit, then the changes in the angle will still be positive. The angle will keep increasing, but the angle reach a point of maximum angle. What do you think should be the speed?
Yes, now it's slow.
You think that is smaller than 1?
Okay, so you said at its maximum,
Hmm?
it would then be equal to the synchronous speed.
Equal to the synchronous speed. Yes, that's going to be the case. Let me go back here. So at this point, after we clear the fault and we are in the green curve with electrical power, then because you have negative acceleration, but because of the inertia, the angle and the speed keeping the angle keep increasing, and we will reach a maximum value for the angle, and at that point, the speed will be 0. So we should think about this situation. So we have the phase plane in which we have the first state variable delta 1, and you have x2, which is omega 1. Well, it's the only generator we have. And then we started here at the angle delta 0. The speed is 1, that's the equilibrium point. But we do have the short circuit. And after we clear the short circuit, this keep increasing until we reach a maximum value, and that maximum value happened here when the speed of the machine is 1 per unit. So this is going to be the maximum value. And then the system, the trajectory will be tracked by this stable focus, and the system should convert back to the equilibrium point. But the point here, at maximum angle, the speed of the machine should be nominal. So that's what we did last time. And I said, well, we can tweak the code we have. And I think that we worked with the code, did we? Did we play with the code last class? Yeah, so we changed the equation to include the new function during the short circuit and after the short circuit. Why they are going to be different? Because the electrical power during the short circuit and after the short circuit are going to be different. What we did before is that the short circuit led to 0 power for the electrical power. And after the fall was clear, we went back to the original electrical power. So we moved from 0 to the blue curve. But now the situation is different. We have an electrical power different from 0 during the short circuit. And after we clear the fall, the topology of the system changed, and we moved to the green curve. So we have to modify the equation, and the differential equation during the short circuit and the differential equation after the short circuit is clear needed to be modified. So we did that, and we got something like this. I don't know if I think that we play with this. The first situation, I consider here a clearing time of 0.37 seconds, and that is going to be the blue curve. That's the same power we used before, 0.5 per unit. And as you can see here, the system gets trapped by the stable focus, and the machine is stable. And this is the plot of the speed and angle in time. For the speed, it's clear you have some oscillation, and this converges to 1. For the angle, because we have this other red curve here, we cannot see it, but it's stable and converges to delta 0. But here also, I consider, what about if the mechanical power is higher now? And I put, instead of 0.5 per unit, I put 1 per unit. Using the same clearing time, and this is what we got. In that case, because you have more mechanical power, then the machine lost stability, rotary angle stability for that clearing time. So what we did, everything that we have done so far, need to be subject to what is the operating point. If you have more mechanical power from the machine, probably that stability margin will get diminished. It will get reduced. So we need to be careful with that. As I said last class on Wednesday, today we're going to talk about a classical technique. This is called the equal area criterion. And this was useful, very important in those times where computers were not used massively. And this was very important for operators to determine roughly whether we were going to operate the machines with a reasonable margin of stability or not. So this technique focuses on the first swing of the oscillation. So I draw here in the phase plane what could be a trajectory when we have stability. So the first swing of the oscillation is from the point where the system is in a steady state, we have a short circuit here. We clear the fault here at this point with a given clearing time, and then the machine at some point stop increasing in the angle and then get trapped by the stable faults. So all this trajectory is known as the first swing. So this technique focuses on that part only. If we make sure that from this point to this point, the system doesn't get any close to the saddle node, then we can guarantee that the machine will be stable. And that's a criterion that they use to determine whether we will have rotor angle stability or not. We're going to make an assumption to make things simple. And that assumption is that we don't have any damping torque or damping power. Okay, so we look at the equation, and because we're using the classical model, we're assuming that the mechanical power is fixed, and the electrical power is given by that when you don't have losses by that sinusoidal function, sine of angle, and multiply by some maximum power will give you the electrical power out of the machine. So if we use the first equation for the angle, we know that on this side we will have the accelerating power, and that accelerating power will be equal to 2 times h multiplied by the acceleration in the machine. Remember that the speed here, omega, is going to be in per unit. So omega is 1 per unit in at the equilibrium point. So here we're going to do a mathematical trick. You have this equation. Basically, we're going to multiply both sides of the equation by the differential of the angle, both sides. Another mathematical trick. This differential in time, we're going to move it to have derivative of the angle with respect to time. So if we do that, then this equation gets converted into this. Why we want to do that? Because we want to include the dynamic of the machine into this relationship. Because the derivative of the angle in time, we know how much it is that. We're using a system with an infinite path that will keep the frequency fixed at the nominal value. So the derivative of the angle is the equation that we have already reviewed so far, which is omega s, and this is in radians per second. So this is going to be 120 pi radians per second, multiplied by the omega, the variable in per unit, minus 1. So that's the derivative of the angle in time. So if we replace that expression here in this equation, we obtain this nice expression. Why this is so nice? Well, this must be true, and if somehow we can enforce this relationship in very particular point in the trajectory of the machine, we will obtain a very nice outcome, and we will get there in a few minutes. So the first thing we're going to do, we're going to convert this differential of the speed into the differential of the changes in the speed. So delta omega is omega minus 1. So at the equilibrium point, delta omega should be 0. Now, because we're adding 1, which is a constant, if you get the derivative of this, then the derivative of delta omega will be the same than the derivative of omega. So in this equation, this differential of omega can be replaced by the differential of delta omega. Now we have this equation. What can we do with this? Well, because this depends on the changes of the omega, the speed, we can first of all get the integral of this. But we're going to get the integral between two particular points, as we will see here. We're going to define these two arbitrary points, point 1 and point 2. We will check that what are these points on. But if we get the integral of this between these 2 points, because this is an integral using the differential of delta omega, this needs to go from delta omega 1 to delta omega 2, from point 1 to point 2. And this side of the equation is the differential of the angle, so this needs to go from delta 1 to delta 2, the angles from those point 1 and 2. Then we get this relationship. This delta omega here, the integral of this, you just have one variable here, so the integral of this will be delta omega squared over 2. That 1/2 get canceled with this 2 here, and the result of that integral is nothing else than this. But this needs to be evaluated between those 2 points. On this side, as we have electrical power, and the electrical power depends on the angle, we don't know yet what is the result of that integral. So for each particular system, we need to solve this integral because we don't know in advance how much is that electrical power. But on this side, this is given already. The result of that integral will be just that expression evaluated between these 2.1 and 2, and we need to evaluate what is the delta omega. So here is the simplification. We are engineers, we try to find simple answers to complex problem, and the 2 points here can be picked in such a way that these 2 points will have a delta omega that is 0. As you can see here, here is the first swing. From the equilibrium point, we have the short circuit. The short circuit is clear, and then the angle reach a maximum angle. So at the equilibrium point here, how much is delta omega? It's at the equilibrium point. Omega is 1. So delta omega is going to be 0. At the end, when we reach that maximum angle, then how much is delta omega? As we discussed before talking about this, the speed at that point is going to be 1 per unit. So once again, delta omega will be 0 at this point. So if we pick these 2 points, 1 and 2, the evaluation of this expression, because delta omega 1 and delta omega 2 are 0, will vanish. So basically what we have obtained is that the integral between these 2 points of the accelerating power must be 0. Yeah. So that's basically the equal area criterion. We haven't discussed yet why equal area, but this is the main relationship that we are getting with this criterion. So for simplification, let's consider the example C. In the example C, we have a short circuit at the bus 1 that set the electrical power to 0 during the short circuit, as you can see here. And then that short circuit gets clear, and we reestablish the electrical power we had before the short circuit. So here you will have clearly 2 different regions. One in which the accelerating power is positive, and another in which the accelerating power is negative. So this is the integral we got before, the integral of the accelerating power between point 1 and point 2, equilibrium point and the maximum angle is this one. But this integral can be split in 2 parts. We can get first the integral of this from delta 0 to the clearing angle, which is here. This is when we clear the fault, plus the integral from the clearing angle to the maximum angle, which is the second part. PM is greater than PE. As a matter of fact, PE is 0, so this is going to be positive. But in this case, as you can see in this plot, PE will be larger than PM. So this part is known as the integral when the accelerating power is positive, or when we have the short circuit. The machine will speed up some. But when we clear the fault, what we expect is that that accelerating power is negative and the machine will be decelerating. So as you can see, as these need to be equal to zeros, then we anticipate from here that this integral is nothing else than the area of this first part when we have the short circuit. And this is the area of the second part when we have clear the fault. This is area 1, this is negative of area 2. So as the two need to be equal to 0, so we conclude that in this case, when you have the first swing, this area 1 must be equal to area 2. And that's the name, equal area criterion. So whatever clearing angle you use here, we can assume a clearing angle. Then by making these two areas equal, then you can determine, for example, what is the maximum angle that the machine will achieve. That's one application of this. Another application of this, and this is what we're going to discuss today, is that we can consider an extreme case. An extreme case is we should never let the angle get any close to the saddle node point. So the extreme case, if this is the electrical power, and this is the mechanical power, and we have the equilibrium point here, and we have a short circuit, so the angle increase. One critical situation will be when the maximum angle that the machine will reach is right there at the saddle node, a little bit before maybe. Because if we let the maximum angle surpass that point, the machine will not be recovered and will be pushed away and be pushed to infinity, and the machine will oscillate. So if we force that as a critical situation, the maximum angle coincide with the point of the saddle node, then we can determine here, and I'm going to draw any clearing angle here, we can determine how much should be that clearing angle that will lead critically to an angle delta max that is a tiny bit before the saddle node. And if we let the protection system to operate at an angle after this, the system will not survive and will be unstable. So that's what engineers many, many decades ago used to prevent this type of behavior. If we let the clearing angle to be way much smaller than this, then we will have some margin and we can guarantee that the machine will be stable. So here I have a few examples. We're going to work on this, but you're going to work on whatever example we don't finish today. And you have 5 problems here. I'm going to explain the last one because this is new. Problem 5.1 and 5.2 are related to the example C. Problem 5.3 and 5.4 is example B. You know those. But problem 5.5 is this situation. I want you to discuss from a rotor angle stability point of view. I want you to discuss whether it would be beneficial to have a substation in the middle of this transmission line. What is going to be the purpose of this substation? Just to split the transmission line in two. But we need to have some breakers. And to operate the breakers, what do we need? We need transformer, PTs, potential transformer, current transformer. We need equipment that can take this measurement and activate the breaker somehow. So we will have a substation in the middle of that transmission line. Is that costly? Yeah, we need to have some investment, and it's not going to be shift probably. But the question is, would it be beneficial from a rotor angle stability to do that? And I wanted to discuss that using the equal area criterion. Okay? So we will start and we will work on this first problem, problem 5.1. So we need to determine what is the critical clearing time if we have a three-phase short circuit at bus 1. We did that by simulation. Do you remember the value? It's hard to remember, but we did the code and we got some result. Let me go back to example C. So for example, C, we have this situation. So what we got, the critical clearing time was 0.48 seconds. We take longer to clear the fault, the system will not survive, will be unstable. So what we are going to do here, use this criterion. Can we determine this analytically? There will be one difference though. When we simulate this, we consider damping. For this technique, we're ignoring damping. So we will be a little bit off. What do you think will be with damping? The critical clearing time will be more or less? More. Okay. So this is going to be on that side. We need to take that into account. We're neglecting damping. That's a worst case scenario, right? It's a worst case scenario. The system might have that. So let's get the data because I don't remember all the data. That's the system and that's the data. So perfect. So I will put that here in the board and we will work on this. So we have a generator, bus 1. We have a transmission line, bus 2, that is an infinite bus. The voltage at bus 2 is 1∠0 per unit. This synchronous generator will have an internal voltage of 1.05 per unit. The internal reactance is 0.2 per unit. The reactance of the line is 0.3 per unit. The inertia is 5 seconds. The mechanical power is 0.5 per unit. I think that we got everything. And the short circuit is right there in bus 1. So what we need to determine now is what is the, let me put here, critical clearing time. That's what we need to determine. Oh. Cancel. Yeah. Okay. So in this situation, then we have worked on this already. And because the system doesn't have any loss, we determine the electrical power for this system. And the electrical power, do you remember the expression for this situation?
Yeah, EV over X equivalent for X total and times the sine of delta.
Sine of delta. So from here, by assuming that we are at the equilibrium point, we can replace the value here. We call this P max, and voltage is 1, E is 1.05, XS is 0.2, XL 0.3, so this is divided by 0.5. So this is 2.1 per unit. That's the maximum power. So by assuming this mechanical power is equal to the electrical power, then we have PM is equal to P max sine of delta 0. We are at the equilibrium point. And therefore, from here, delta 0 should be arc sine of PM over P max. So PM is 0.5 and P max is 2.1. So from here, we can determine the angle. That's the first point. So 0.5 divided by 2.1, and then we get the arc sine of that. So what we got for this angle is 0.2404 radians. So that's the equilibrium point. If this is 2, maybe here is the mechanical power, which is 0.5, which is the mechanical power. And this point right here is delta 0. Because here you have pi, and by this symmetry, then the point here at the saddle node is going to be pi minus delta 0. But the system starts here. The system is at the equilibrium point. So when we clear the fault, then the power immediately is sent to 0. The speed and the angle will increase because we will have a positive accelerating power. But we want the maximum angle to reach the maximum possible angle before we lost stability, which is at this point, the saddle node. So if that is the situation by the equal area criterion, here we will have an area that at some point here will split the graphical description here, and we'll define area 1 here that must be equal to the area 2. The integral of the accelerating power, when the accelerating power is positive, must be equal to the area of the decelerating power when the decelerating power is also positive. So area 1 must be equal to area 2. And this is going to be the critical clearing angle. Okay? So we calculate this area, A1. This is easy because the electrical power is 0, the mechanical power is constant. So the integral of this will be just PM dt, the differential of the angle. So the solution for this is PM delta evaluated on these limits. So basically, this area 1 is PM multiplied by the difference of the clearing critical angle minus delta 0. That's the first area. The second area, area 2, will be the integral of this part. This integral needs to be positive. So instead of getting the mechanical power minus the electrical power, here we need to get the electrical power minus the mechanical power. So on this part, we will have the integral from the critical clearing angle to the maximum angle that will correspond to the angle at the saddle node, which is pi minus delta zero, of the electrical power, which is P max sine of delta, minus the mechanical power. So we need to get the integral of this. The first part is the integral of P max sine of delta. So the integral of sine of delta is negative cosine of delta. And this will be evaluated between these 2 points. The second part is constant. So here we have negative PM evaluated on this limit. So you have delta max minus delta clearing, critical delta clearing, critical level. So that's a solution for area 2. Okay. So to apply the equal area criterion, A1 must be equal to A2. A1, we said that was PM multiplied by the critical clearing angle minus delta zero. And this must be equal to the second area, which is going to be PM cosine of critical clearing angle minus cosine of delta zero. Is that right? Yeah. And the last one, which is the constant term. So the constant term will be P max multiplied by delta max plus this PM, not P max, PM, and the other is PM delta critical clearing angle. Let me check. This becomes positive, and the other is negative. Yeah. So as you can see here, there is one term that gets canceled. This PM delta critical clearing angle. This will get canceled with this one on that side. Here you will have PM, negative PM delta zero. Here, negative PM delta max. So we need to consider that. And of course, this part. What is unknown for us? We're trying to find that value. So there must be an angle, a critical clearing angle that will make these equal. So the areas A1 and A2 are equal. So we solve for that angle. So we're going to send everything here to the other side of the equation. Well, we can put this on the left. So we have PM cosine of the critical clearing angle must be equal to PM. This is going to be negative, but this one on the other side will become positive. So this is delta max minus delta zero. So we have already these two terms. We just need to send these to the other side. And that is going to be plus PM cosine of delta zero. So we solve for the critical clearing angle, which is going to be arc cosine of all of this. There is something off here. This is P max, right? Yes. P max. On this side, we have P max. And oh, this is fine. This is P max. So it's going to be PM delta max minus delta zero plus P max cosine of delta zero, all divided by P max. So we evaluate this. And we see what we obtain. We can put these numbers here so we don't get confused. This one is 0.5 multiplied by delta max, which is pi minus delta zero. So basically here we have 0.5 multiplied by pi minus 2 delta zero. And on this side we have 2.1 cosine of delta zero divided by 2.1. So delta zero is 0.2404 radians. So let's see what we get. So this part is 1.6048. And the arc cosine of this, oops, that's not right. It needs to be less. Let me do it again. 0.5 pi and pi 2 times 0.2404 there, pi minus that, half. One cosine of that. We're missing a negative sign here, are we? Send this to this side. There is an error there, I guess. P max sine of delta minus Pm. We get the integral, this is the negative of this. P max cosine of delta max and plus the critical value. Okay, and this one is flipped. So this is negative Pm delta max and positive Pm delta critical clearing time. Now you can see that better from your seat. We copy that and put it right here. Pm delta max plus Pm delta critical clearing angle. Those two are fine. Ooh, here's the problem. This is negative or not? Yeah, that's wrong, because this is delta max. That's fine. Are you following?
Yeah.
Yeah, is that better? That's delta max. And area 1, I think it's fine. Pm delta critical clearing angle minus delta 0. So that was the problem right here. So when we send these to the other side, then this is not delta 0. This is a maximum angle. And therefore, this is maximum angle. And the maximum angle is at the saddle node, pi minus delta 0. That's much better. Yeah. So this number cannot be greater than 1. And we do it again. 0.5 pi now it's much better. So this is going to be negative of 0.3377. And the arc cosine of this is much better, is 19153 radians. Which is about 109.74 degrees. Okay. We go to the other side. Yeah. So I will erase this part here. So we need to get the critical clearing time, but we got the critical clearing angle. So here, what we have is the two differential equations. This is one. and the equation for angle, for speed, is going to be just PM over 2h. So from here, the speed in time is going to be an initial speed, which is 1, plus PM 2h, is just the integral of this, times t. That's the expression for the speed. If we replace that over here, then we have that 1 will get canceled here. And you just have omega s multiplied by this. Oops, omega s PM over 2h times t. And now we can get the integral of these to obtain the angle. So the angle will be a constant, the angle at time 0, which is delta 0, plus the integral in time of this. This depends on t. So the integral of this is omega s PM t squared over 2. So that will lead to 4h t squared. So that's how the angle should change in time. Yeah. So with that expression, we can finally determine what is the critical clearing time. So if we, as we know the explicit solution for the angle, we can replace here when delta t is equal to the critical clearing angle, and we can solve for the critical clearing time. So we do that. So we will make delta t critical clearing time is when this is equal to critical clearing angle. And this is equal to delta 0 plus omega s Tm over 2h t critical clearing time is squared. So from here, the critical clearing time is the square root of the critical clearing angle minus delta 0 multiplied by 2h divided by omega s Pm. Okay? The board is horrible.
Yeah, it is.
How can I clean this board?
Got like expo spray.
Nope. Why do they put this board here? What about this thing?
I tried. It gets it a little, but not very well. But I was going to ask, in the top right, you wrote over 4H, but then you wrote over 2H over here.
Okay. Oh, yeah. Thank you.
Yeah. Okay.
This one, because of this, yes. Oh, my.
And then your research just makes it bad again.
Yeah. I'm sorry. I'm very sorry. So T critical clearing time square root of yeah. Oh my. Well, I will ask for help. Let's change the board. How is that? And this is 4H. 4H. I don't know if this can be seen from the video or not. Yeah. Well, we can replace the values and see what we get. What time is it? Ooh, we're way past the time. So we can do this. Plug the numbers. We have all this value. We have calculated the critical steering angle. We got the initial angle, H, all the data. See how much you get, and play with the code and see if we got anything similar to this or not. They are not going to be the same. Why not? Because of the damping torque. We use the damping torque. What we can do to verify this? Well, in the code, let's eliminate the damping torque and see if we get any close. The result should be very close, okay? So, final thing, a reminder, please work on the problem that I have in the slide. There are 5 problems, let's work on all of that. On the way back from the spring break, we can discuss, we can work a little bit more, some of those, and if you have questions. Yeah, but that should be the end of this chapter. On the way back from the spring break, we will talk about a better model for the synchronous generator and how we simulate multiple machines. Yeah? And then we will move ahead in the program. Any questions? No?
Yeah, actually, when we have a d omega dt equals pm over 2h, is that or we're not considering the rest of the equation because we're at the
The electrical power is 0, and we are ignoring the damping power.
okay.
That's the assumption.
Okay, and also, so are we integrating with respect to t or omega when we integrate?
This is a derivative with respect to time, so we integrate with respect to time.
So where do you get the
This
1
solution.
plus?
It's a constant. That's the initial speed.
Oh,
The integral will come with a constant. So that's the speed we have at time 0.
I see.
The same thing will happen here for the angle. We get the integral. This is the angle at time 0. That's the equilibrium point.
And so these equations for during the fault period.
Yes. Yeah, that's for the full period. We can easily calculate it, because it's a short circuit with electrical power equal to 0.
So we can choose that to check it.
Yeah. Okay, guys, thank you so much.